often what we see in EAS type reactions is benzene with more than one substituent. So we've seen the effect of having activating and deactivating groups. What happens if we have more than one group on a ring? Well, it turns out that when we put more than one group on a ring, those groups can either complement each other or there can be conflicts. So let's take benzene here. Let's put a methyl group and another methyl group here. And I want to just put a box around this guy here, make it red, and then down here below we'll do a little triangle around this other methyl group. Now let's take a look at what this reaction would give us if we were to nitrate it. So HNO3 H2SO4. Now we know that both of these groups, right, these alkyl groups, are activating OP directors, right? Both of those groups. So there's a couple ways of doing this, but one way to illustrate this point is to look at this. Well, if it's activating OP, if we look at this red guy, right, adjacent to that is ortho. So that's the red's referring to the position relative to the CH3 that's in the red box. That's meta, we can't put anything there. Down here is para, right, to that. And then over here, we are ortho to this, okay? Now, what about this triangle? So if we look over here, the triangle, comma, is ortho right there, right? Across, right over here, we are para, and over here, we are ortho. So we're ortho, para, directing, and those three positions are all ortho, or a mixture of ortho and para. And then to point out over here, we're meta and we're meta. So those are two bad places, right? We would not want to substitute there. So these are complementary to each other. So our final product here is going to be our CH3 here, another CH3, and then at the OO, we'll get an NO2, and also at that ortho-para position, right? So CH3 down here, and then we can put an NO2 right there. That's true that we can also react it at this position, right? If we look at the original structure, so all three of these will react, but if we react it at that top left corner here, that's the same as doing this corner down there. So we get a repetition of products there. So we only want two, only unique products. All right, so let's look at another one here together. What about para-nitrotoluene? So para-nitrotoluene, CH3 here, NO2 down there, right? Now, let's do the same thing. So this guy right here will make our red guy, and then this guy down here will highlight as being our blue. Now we know that this group up here, that group is activating, and it's an OP director. Down here, we're deactivating, and we're an M director. So let's go through and figure this out. Relative to this red boxed CH3, we're ortho, we're meta, and we're ortho. Right? Relative to the nitro group over here, we're ortho, right? We're meta, we are ortho, and we are meta here. So we go through and we take a look at this with our nitration, for example, HNO3, H2SO4. Well, what happens here? Well, ortho is good, right, for the red, because we're ortho directing, right? So that's good. And meta is good also, right, for the deactivating group. So this group right here, this position is good because we're ortho here, but meta there. And same thing over on this side. Ortho, meta over here. So those positions are where we want to nitrate it. Now, when we go through and write our product out for this, now when we go through and write our product out, there's potentially two spots that could react, but they're going to give the same product. So we just need to write one of them. So there's your nitro group there. That's your only product. So this is how we treat this situation. We just look at the substituents and we see if they're complementary, and if they are, then it's pretty easy. They reinforce each other. Now, on the other side, we have conflicts. Now, conflicts are easy to resolve also. So this little statement here is going to help us survive chapter 17. It says, when there is a conflict between an activating group and a deactivating group, usually, and this is pretty much all the time, the stronger activating group dominates the orientation of substitution. So we have three types of substituents, right? Powerful OP directors with lone pairs, negative charges. Moderate OP directors such as alkyl groups. And also meta directors here too. Okay, so let's take a look at a couple of examples. So let's look at orthoxylene. So xylene is like a double toluene. So it's a benzene with two methyls. So here's a CH3 and another CH3. Right. So we go through and think of this, and if we were to nitrate this, so HNO3, H2SO4, where would we do this? Well, this position here is meta to that, right? So you're meta here, but you're ortho to this. So this is meta ortho. Over here, you're para or meta, right? Over here, you are meta or para, and here you are ortho and meta. There's a problem everywhere. So in this situation, we're going to nitrate it at these positions because there's no clear winner. So in this case, there's no best place. There's just a problem at every place, essentially. Well, if we nitrated it right here, that would give us the same product. And so this position here and that position would give you the same product, right? And then those other sets down here, this guy here and that guy down there, would give you the same product too. So we're just going to get two products here. So here's your CH3s with the xylene, and then we can come over here, right, and we can put it wherever we want to, so put it down here. So we get two products. So the other positions would still get nitrated, but they're just duplicate positions. All right, so let's take a look at another example here. So let's put an O here, CH3. Let's nitrate it. Right, so by itself, that's the easy one, ortho-para directing, right? So we get two products. But let's make it more interesting. Let's put an NO2 group here. Okay, so when we look at a problem like this, this is how we would approach it. We'd say, okay, this group up here is activating, OP. This group here, deactivating, M director. Well, we had just said a second ago that activators beat deactivators. So this is going to be the loudest voice that directs the orientation of substitution here. So what that means is that ortho and para are going to be our products here. Right? So simply put here, this is our activator, and it wins. Okay, so we'll get 3 products. So you get your methoxy group of anisole in there, your NO2. So we're going to get this guy. Right, this product, and then the other product we get will be right, and it would be here. Right, so ortho and para to the methoxy group. Right, so just as another little exercise here, what about this? So what if we took that molecule and we did something like that? So put an alkyl group here, and then how about this? Put an oxygen here, and then that. So let's just think what would happen in general if we were to add like an electrophile. Where would it go? All right, well, this is at activator, right? It's O, P director. This group is actually a deactivating group. So dipole getting pulled this way. Delta plus, it's a carbonyl. Remember we said aldehydes of carbonyls? Our carbonyls are going to be deactivating, right? So delta plus there. So this is a deactivating group. And then this is a lone pair bearing atom. So this is an activating group. So it turns out that this is going to be your director because it's a stronger activator than an alkyl group. A lone pair bearing atom is a stronger activator. So if we're just kind of pointing where this is going to react, that's ortho, so it will react here. And then para, so ortho and para to this. So then the other place would be right there, which is your para position, right? So at this position, at that position, that's where we see those electrophiles essentially going.